Module 4 of Chapter 20 turns to geometric Brownian motion, which we will see and have already seen is the model of choice for stock prices, and indeed the model that underlies the Black-Scholes option pricing formulas, and is the model of option prices to which our binomial lattices converge when the number of steps in the lattice grows without bound. So this is the stock price process of choice. So geometric Brownian motion is a process that is a simple version of, in general, what's called an Ito process. I made the point in a prior module that one could imagine a process dx where the drift term could be a function of x and t, and you could also have the variability term also be a function of the value of x and time, dz. So geometric Brownian motion is a simple example, if you will, of a general Ito process whereby we hypothesize that this drift function is simply the constant alpha times x, and this volatility function is simply a constant sigma times x. And so here you can also think of this as arithmetic Brownian motion, whereby instead of having a for a drift we use ax, or instead of using sigma for a vol we use sigma x. So this is a form of geometric Brownian motion. It can also be expressed this way. We've seen this before, that sometimes geometric Brownian motion is expressed in terms of the ratio of dx to x, and you can see that this is arithmetic Brownian motion. So the ratio of dx to x is arithmetic Brownian motion, if you want to think of it that way. But importantly, the change in x is proportional to x. And the reason for that, I mean, just to be clear, to make sure that that point is clear, we can also say that the change in x is equal to alpha dt plus sigma dz times x. So that's clear, hopefully, from equation 20.11, but just to be more explicit, it's saying that at every point in time the change in x is proportional to x, and the proportionality factor has two components. It has a fixed drift component and a variable component. So at each point in time, change in x is proportional to x, and the proportionality factor has a variability to it. Because we know that arithmetic Brownian motion is normally distributed, we can convert that earlier equation to observing that the ratio of dx to x, if we look at the ratio of how much x changed to its starting value at any point in time, it's going to be normally distributed, and it's normally distributed with a mean and a variance that's proportional to the length and time. This should look familiar, that this is the comparable model. This is the generalization of what we saw earlier with Brownian motion, where Brownian motion's variance was, in fact, on any interval of time, proportional to dt. So here we see that same feature, mean and variance proportional to dt. There is an integral representation of this, and this is a case where both integrals are quite complicated. This is a stochastic integral, again, a very complicated version. This is actually technically not a stochastic integral. This is, in fact, a Riemann integral from calculus, but one has to be very careful in how it's evaluated because x of t is so complicated. And in particular, x of t is a process. And namely, what this is saying is that if you look at any path of x's, we can integrate them in a Riemann way and integrate this term in the stochastic way, and those two integrals will give us the total change in x. So there is a definition of integral which makes this work.